Hello and welcome to day 21 of Advent of Code 2024. So this day is called Keypad Conundrum. And in this puzzle we need to save one of the historians who has been locked into a room, and you need to type in a code on a numeric keypad. But unfortunately the room outside that door is currently depressurized, so a robot needs to be sent in instead. That robot is steered by this directional keypad, and when the robot arrives, its robotic arm is pointed at the A button, and the A button means that it actually pushes down on one of these buttons when its arm is over one of those areas. And to make the robot do this, type type 029A on the numeric keypad. The robot must do these moves. Another layer of difficulty is that the area containing this directional keypad remote control is currently experiencing high levels of radiation, and nobody can go near it. A robot needs to be sent in instead. So that robot is also controlled by a directional keypad. So that robot will in turn control the other robot who stands in front of the numeric keypad. And the last layer of it will be our protagonist will have to steer that second robot with its numerical, or with its directional keypad. So that is basically what this problem is about. So we need to so here we can see the example this is kind of the outer layer. The outer layer is this row here. The second layer is this. That's the middle robot, so to speak. So this is you, or our protagonist, who do these moves. These moves run the So this is, as I said here, this is our protagonist who inputs these moves. This is the second robot, the middle robot, so to speak, who in turn do these moves to let the last robot do these moves, and that will cause it to input this code on the numeric keypad. And to unlock the door, we need to input 5 codes, and these are examples of that. And for these examples, these are kind of one of the best, shortest paths we can do to make all the robots layers do this. And we need to take the length of this shortest sequence. We need to take the numeric part of the code, which is, for the first one is 29, because we are ignoring leading zeros, and the length is for the first is 68. So we multiply that with the numerical part of the code. We do that for each code and sum that up together, and we should get this 12,006 or 1263.84, which will be our test or example data value. So so let's go to the code then. So for this code, I have actually had I've had a lot of issues with this code. I struggled with it pretty bad, and finally I got it to work. So it's not totally perfect yet, but I will show you my solution for this. So and it's quite a lot of code as well. So I will just kind of copy the code into this blank slate, and and explain a little bit what the thought about it is. So first we need to define our keypads, because this will be essentially our grids. But where we will do kind of pathfinding exploration on these small grids, so to speak. We need to store those sequences for, and this will be exactly our length from different keys on these keypads. So we will have a kind of a dictionary with a from and to character and list of kind of the sequences. So for instance, if one needs to go A to 0, we will have this as a character. Then we will go, if we want to go up, we need to have this character. So we will kind of build on that string to reach, and then whenever we want to click on the A button, that's what we need to do when we have reached a button that we want to click on. And that's the same for these directional keypads. So we want to compute these sequences beforehand, so to speak. So we will kind of find all these shortest sequences before we do our actual calculation of the codes. So let me just bring in these methods here so that we get kind of the whole story. Yeah, so let's begin here. So we have these compute sequences. We will send in either of these keypads because it's the same actually. Well, they're not the same, but we will kind of treat them the same. So we will loop through each character of these keypads. So we will loop to the first one and the second one, and kind of do it in tandem in this way. So we will have our shortest sequences dictionary. We will initialize that, and this will be kind of the first time we reach that position. So if this is actually the same, if this character and this character is the same, then we are in the same. Then we actually are at our intended destination, and then we will actually add an A, because then we want to push the button. But we will not break. We will just continue in this, because we will do a breadth first search, and we will want to find all the best paths, all the shortest paths. So if we don't have this, we will land on this method. So we will find the shortest sequence, and here we will do kind of a more traditional way of breadth first search. So we will kind of take out the from position and the to position. We will also have the Manhattan distance of those positions. That will be kind of our shortest path. Then we will have a queue with a row and column and our string sequence, and also we will enqueue that. So if we arrive at our intended position, we will kind of first we check if we actually have this key. Maybe this is actually unnecessary because we actually initialize it here, but yeah, I haven't changed this code too much from when I actually solved this issue, so I will probably clean this a little bit up before I push this to my GitHub. But yeah, so we will actually add this the sequence that was before it, but we we will add the A at the last, because there will always be an A at the last, as a last thing in every sequence, because we want to push the button, and that's what the A means. Then we will also continue here. We will not break as you normally do. That's when you do breadth first or any pathfinding algorithm thing. We will normally break when we reach our end position, but we will not do this here. We'll just continue there. And then we will also check that the length of our sequence, if that is greater or equal to the shortest path, then we were not interested in it, because then it's probably that means that this is a longer path, a longer sequence. So we're not interested in. We will find the shortest paths. Okay, so and as a last stop, we will do our normal directional kind of search. So we will have our direction row and column. We will move up, we move right, down, and left. We will check if we are inbounds on the grid. We will check that we are not on this pound sign. Yeah, I actually forgot that, because in the specified in the specification, this is kind of an empty space in these keypads, but in my version I've actually added a pound sign to these empty spaces. That's just so I can keep track of them by doing this. Then we will if we pass all these check, we want to enqueue this as our next position, and then we want to do a switch on the direction so that we get the correct directional char. Then we will add that to our sequence, and then we will kind of move to the next. And this will be our kind of pathfinding algorithm thing. So to use this, then in the before we do our actual computation of our codes, we will initialize these. We will initialize both the numeric and the directional keypad, and then we will read in our code. Then we will define another dictionary that we have as a this will be kind of our memorization dictionary. Then we want the total value, that we will collect our total value. Yeah, we will also use the test input here. So we want to verify the result in that. So we do for each of all our codes. So we yeah, exactly. So this is what we're going to do, and in the end we will have kind of our part 1 value, but we must implement this method here. So this is our kind of a last thing we do here, and I kind of this gives us actually a little bit away for the part 2 of this problem, but I kind of did this method when I did part 1 for this problem. I kind of used this kind of memorization technique because I usually want to do that when we're doing recursion, but I wouldn't have to do it for the part 1 of this problem. But it was definitely necessary for part 2. But then when I did it like this, part 2 was just a matter of adding a few lines of code. So my completion time for part 1 was like 2 hours and 21 minutes, and my completion time for part 2, inclusive part 2, was kind of 5 minutes later or something, because that's so it kind of pays off to do part 1 properly if you want to do part 2 fast. Yeah. So in this sense, we will only go three layers deep in our recursion. But let's see what this method does then. Well, at first we will always check our shortest sequence memo if we have the value. If we have it, we'll just return our memo. We will not do another recursive jump down the line. If we have reached our max depth, which will be 3 for this, then we kind of have reached the last robot in our list. We will add this to our memorization dictionary. We will then return this code, and then we will kind of start our exploration algorithm. So we will always start at an A shard. All robots has its start position over the A button in their directional their directional keypads, and we want to keep track of the best length, because so we will have this best length initialized up here. Then we will start to do for each or of every character in the code. We will kind of pick out from our shortest sequences dictionary. We will pick out all the sequences that we have stored previously. We then do our current best, which will initialize to the maximum value of this long variable. Then we will do for each character in this shortest sequence. We then do another kind of our recursive jump here. We increase the depth. We also keep our max depth with us. And if the length that is returned, if the current best is greater than the length, then the length becomes the new current best. Now we'll kind of add it to our best length, and then our previous char will also be set to the current char. Then at the end here we will add it to our memo again, and we will return the best length in the end. So this is our kind of our method. So let's run this part 1 of this problem here. So let's see what we get here. So 126384. I believe that this is what we should aim for, yeah. And we can actually just actually check with our real data as well. So we still have the correct result, and this will be 188384. That is what the value was for my input data. Yeah. So part 2 here, as I already kind of gave it away, it is actually more or less the same thing, but now they added 25 directional keypads on top of that robot you are using. So it will be kind of 25 robots and you. And that kind of, if we hadn't used memorization for our part 1, we would definitely have had to use it for our part 2. So the thing we need to do here, we need to reset our shortest sequence memo, because now we're going to do a new call to this method. We will reset our total variable, and then we will call this method and then send in 26 instead, and we will have our part 2 value. So for part 2 we are not getting any what the value should be for our example data, so we have to go by this data here. So that's actually more or less part 2 of this problem, and we have our, let's see, 232, 832 on the end. That should be our 232 and 832 on the end. Yeah, that's the correct value. So this has been a pretty fun puzzle, I think, and I know many people have problems with this, and definitely the difficulty level has definitely been extended, or it has been increased, definitely. So let's see what happens tomorrow. Maybe we will get kind of a little bit of a break tomorrow, I will hope, because I've kind of, I spent a couple of hours with this, and also have spent a few hours more kind of cleaning it up a little bit, and so I hope tomorrow will be a little bit easier, but I do enjoy these kind of problems, because it should be demanding. I mean, now we kind of coming into the home stretch of this advent of code. So 22, 23, 24, 25 should be kind of harder, more difficult problems. But let's see. So and we will see each other tomorrow then. So bye bye.